Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
CMOS logic gates are widely used in low-power and fast-switching applications. The dynamic modes of operation of a CMOS gate involves in charging and discharging of parasitic and load capacitances that results in propagation delay. By using power delay product parameter, low-power switching gate performance is assessed and optimized. Power delay product defines the energy efficiency of a logic gate that specifies the energy consumed for a single switching event. In this video, we will discuss a CMOS inverter, parasitic delays and static and dynamic power dissipation parameters, from which product delay parameter can be evolved. So, let's get started. A metal oxide semiconductor field effect transistor is key component employed in switching and amplification applications. It is made up of source, drain, gate, substrate and a thin oxide layer. Most transistor structure is fabricated using several overlapping and isolated layers that results in creation of parasitic resistance and capacitances, which in turn limit the device performance. A complementary N and PMOS transistors are of two types. The enhancement mode FET is normally off and needs gate voltage to turn on, whereas a depletion MOSFET is normally on and requires gate voltage to turn off. A MOSFET is characterized by high input impedance, fast switching speed and low power consumption. Figure shows the transconductance and output VI characteristics of an enhancement type and MOSFET. The transfer characteristic displays in-out transconductance gain relationship. Enhancement mode MOSFET is normally in off state and needs minimum gate threshold voltage VT to conduction mode. MOSFET output characteristics as shown can be divided into three regions of operation. For gate voltage less than the threshold voltage, FET is in off state and no conduction takes place. For gate voltage greater than the threshold and drain source voltage less than VGS-VT, the device operates in ohmic state and is popularly used as variable resistor in analog designs. For gate voltage greater than the threshold and drain source voltage greater than VGS-VT, FET operates in saturation mode and acts as constant current source. A thin silicon dioxide layer sandwiched between a poly and a silicon substrate forms a FET gate capacitor. A MOSFET is a voltage-operated device, wherein the gate capacitor dumps charges into channel area and are collected by source drain voltage. The gate length is dictated by the technology feature size, along with the width dictates the FET current capability. The drain current depends on material properties like carrier mobility, oxide thickness, permittivity and also on physical gate dimension ratio of width to length. The drain current equations for different operating regions are shown in the figure. The current drive strength of an inverter depends on MOSFET structural properties like carrier mobility, oxide permeability, thin oxide thickness, length, and width of the gate. The drive strength is defined in terms of fan-out capability. CMOS inverter, due to gate capacitive input nature, draws very low current and offers high input impedance. In logical high output state, PMOS produces the source current IOH and charges the load capacitor. In logical low state, NMOS produces sink current IOL and discharges the load capacitor. Thus, charging and discharging of load capacitor produces the output switching voltage. Inverter under dynamic operation also produces dynamic, short circuit, and crowbar currents. A CMOS inverter is built using complementary P and N-MOS field effect transistors. During switching, inverter undergoes various operating states and are represented through a voltage and current transfer characteristics. The voltage transfer characteristic Vt of a CMOS inverter shows how the output voltage Vout changes as a function of the input voltage Vin. The current transfer characteristic CTC describes the current flowing through the circuit as a function of Vin. As shown in the figure, transfer characteristic can be divided into 5 regions of operation. Region 1, for input less than transistor threshold voltage, the output is at high level. Region 2, for input at VL, reaches NMOS threshold voltage, NMOS starts turning on and output will be at VOH. The transfer characteristics represents a slope of unity and the output voltage starts decreasing. Region 3, rising input voltage equals the falling output voltage as a gate threshold VTH point. Inverter with both transistor operating in saturation mode conduct maximum current IDD. The inverter with high gain starts acting as an amplifier. Region 4, with input at VIH, that reaches VDD-VTPP, PMOS starts turning off and the output reaches VOL. The transfer curve slope reaches unity. Region 5, for input greater than VIH, the out starts further decreasing but slowly. The power dissipation in a CMOS inverter is influenced by several factors, categorized as indicated below. Dynamic power dissipation occurs due to switching activity of charging and discharging of capacitance currents and the output voltage switching between high and low states. Short-circuit power dissipation occurs in switching transition, during which both NMOS and PMOS transistors are momentarily on, causing large current conduction between supply rails VDD. Static power dissipation occurs when the inverter is in a steady state that is not transition, due to leakage currents like subthreshold, gate, junction leakage, etc. This becomes significant during scaled-down nanotechnologies. Shrinking of semiconductor technology, often referred to as scaling, is implemented to build more transistors in a given die area. Along with many advantages, shrinking also has some negative effects like increased parasitic, leakage currents, static power dissipation, etc. Various leakage currents that exist in FET and contribute to the static power dissipation are discussed below. Device operating in cutoff region with weak inversion layer create minority carriers that diffuse across the channel and form subthreshold leakage current. The silicon substrates, structural defects like surface roughness, traps, contamination, imperfections, etc., cause substrate leakage current. FET operating in current saturation mode will have drain to substrate and source to substrate junctions reverse biased and creates junction or reverse bias leakage current. For thin gate oxide layers like less than 2 nanometers, quantum mechanical phenomenon occurs wherein electrons tunnel through the thin gate oxide layer and create tunneling current. When the depletion region of the drain extends too close to the source, creates a current flow that has no gate control and is called punch-through leakage. This phenomenon is prominent in short-channel device. Sum of all the leakage currents put together contributes to the static power dissipation. As shown in the figure, capacitive load switching creates charge and discharge current transitions. The overlap of switching output voltage and current transition produces dynamic power dissipation. Each charging and discharge cycle of load capacitor CL, switching at frequency of F, produces energy switching per each transition and results in dynamic power dissipation. If the switching does not take place for every cycle, the duty cycle factor alpha is to be taken into account. Dynamic power is computed as product of load capacitance, frequency, duty factor, and square of supply voltage. Short-circuit current of a CMOS inverter occurs during the switching transition, when both N and PMOS transistors for very short period will be in on state and conducts current across the supply. During inverter transition period, due to poor mobility of holes, the PMOS switches off slowly. That is, even after switch off, for a short period it continues be partially in on state. During this period, NMOS being a fast device, it switches on faster. During this transition, for a very short period, both transistors will be in conduction state and conduct current, resulting in short-circuit power dissipation. Short-circuit power dissipation, in addition to slow input rise and fall transition, depends on increased power supply voltage, capacitive load, threshold voltage of most transistors. Parasitic capacitances in MOSFET arise due to mismatch of the device physical layer structure and significantly affect the performance. In MOSFET fabrication process, variations in processing equipment, mask alignment etc. causes mismatch in process layers creation and result in device parasitic capacitances. For example, the gate process layer misalignment to source and drain layers creates gate source drain parasitic capacitances. The MOSFET structure is shown in the figure, has parasitic of source to body, drain to body, source to gate, drain to gate parasitic capacitances. These FET parasitic capacitances directly impact switching speed, power dissipation, and high-frequency performance. Parasitic capacitances in MOSFETs originate from the gate, drain, source, and interconnects. The key capacitances affecting CMOS inverter performance are gate-to-source drain and body-to-source drain capacitances. Figure 1 shows inverter with all MOSFET parasitic. Normally FETs are used with body connected to source terminal and, hence CBS can be ignored. CGD is the capacitance prevailing across voltage gain terminals and is known as Miller capacitance. CGD across gain terminals can be further simplified by transforming CGD onto the input side as voltage gain times CGD. Parasitic can be now represented on input side as Cn is sum of CGB and voltage gain times CGD. The output capacitance Cout can be represented as equal to CDS. Figure 2 presents CMOS transistor level inverter with simplified MOSFET parasitic capacitances of Cn and Cout. Figure 3 shows gate level inverter with input Cn and output capacitance Cout. These parasitic create impact on inverter, power parameters and timing parameters like propagation delay, dynamic power, short circuit current etc. CMOS inverter switch model with resistive and capacitive parasitic is shown in the figure 1. Inverter in-out switching waveforms are shown in the figure 2. The transition and propagation timing delays created are due to parasitic R and C elements. The transition delays are normally accounted as part of propagation delays. The average propagation delay is defined as the average of TPHL and TPLH delays. The cell delay is shown in the figure 3, is the sum of intrinsic and load-dependent delay. The power delay product PDP is an important metric of a semiconductor logic gate design, particularly for high energy efficiency, low power applications. It is crucial for understanding the dynamic performance of energy efficiency digital devices. PDP specifies the energy efficiency of a gate that specifies the energy consumption for a single switching event. This parameter will balance a trade-off between delay and power consumption of the gate. PDP is not specified in a commercial datasheet, but can be derived from the datasheet parameters and from characteristic curves. This parameter helps the designer in selecting an appropriate lower nanotechnology nodes devices that meet the delay and power dissipation parameters. Total power dissipation of a logic gate is the sum of static, dynamic and short-circuit power dissipation. The mathematical relation of total power dissipation and PDP computation is presented. Thanks for your time. Hope this video has been helpful in appreciating the CMOS logic gates delay, power dissipation characteristics and their energy efficiency assessment parameter, PDP. Thanking you once again and hope to meet you in upcoming video. Bye for now.